All right, we're going to finish up inductive reasoning by looking at causal arguments. These are inductive arguments in which the conclusion is a causal claim. In other words, a conclusion that talks about or references a cause and effect relationship. Okay, so to put it another way, causal arguments, they're inductive. They have causal claims, a claim about cause and effect as their conclusion. So for instance, let's say that I have a philosophy class, call it Philo 49, and that the average for one section on the third exam was 10 points higher than an average in another section. Let's say that this unprecedented average was one that I had never seen before. So what could explain one section of a class I'm teaching doing better than all the other sections of the term, and even better than all the sections I've ever taught? Well, one factor or cause, maybe that section was just more intelligent. Maybe that section of students was just more diligent and you guys studied more. Maybe you guys were clever and you cheated. Maybe you bribed me. So you slipped me, so $100 bills, the Benjamins. It could be all sorts of things. So we're looking for the cause of this average that was unprecedented. Okay, so that's the example of a causal argument. Now let's jump into how we classify them. Well, with all these arguments, what we're going to see is either a common event or an exclusive event. An event is common if it's something that happened to everyone, or it's recurring, it's something that happens over and over again. Whereas an exclusive event is something out of the blue, it's atypical, it's out of the ordinary, or maybe it's just an event that stands out. So in the third exam example, the section doing better than the rest of the other sections is something that's different. It's something that stands out. It's an exclusive event. And keep in mind that both, whether it's a common event or an exclusive event, it's an effect, right? So the higher average is the effect. And when we hypothesize about you guys being more intelligent or bribing me, we were looking at potential causes. So whenever there's a common or exclusive event, then we want to be good detectives and try to figure out and identify what the cause of the effect was. If we have an exclusive event, then the cause is going to be known as the relevant difference, and we are going to be talking about relevant difference reasoning. Okay, so these are all the potential causes of the exclusive event. The one that's the correct cause, we name the relevant difference. So the exclusive event was the effect, and the relevant difference is the cause of this exclusive event. And that sort of relationship, as I mentioned, indicates relevant different reasoning. So this is opposed to common thread reasoning. Here's another example. Let's say that we have a pizza party after our last exam. So I could ask you guys what kind of toppings you want, which restaurant. And let's say we make a decision about this and we decide to go with, I don't know, we go with Round Table. And we have our last exam, and then the pizzas come and we have a pizza party and we're socializing and laughing about all the good times, blah, blah, blah. But then something strange happens. Perhaps after enjoying this pizza, one by one, everyone starts getting sick. So one person says, oh, right, I don't feel good, and you leave the classroom, and then another person says the same thing, and then one by one, we hop on the modus ponens express straight for Puke City. So in this case, everyone getting sick, it's something that's common, right? It happens to everyone. As opposed to the earlier example where the high average is something that's atypical. So we have a common event, and we're looking for the cause. The cause of a common event we call the common thread. Okay, so what are the possible causes? Well, we all ate the pizza. That would be our first guess, right? That's why everyone got sick. But it could turn out to be something that we didn't really suspect. Maybe it was something that we drank, right? Maybe it was some, it was the yellow number 5 or the red 40 that was in the Mountain Dew. Or maybe it was something different or strange. Maybe there was like something with the ventilation. So whatever it was, that is the common thread. Remember, the common thread is the cause, the common event is the effect. In this case, the effect is getting sick. That's the common event. And the real cause is the common thread. And maybe it was something in the ventilation. But remember, for relevant difference reasoning, it's the relevant difference that causes an exclusive event. So it was the studying or the cheating that caused the higher than normal average, the relevant difference that caused the exclusive event. And for common thread reasoning, it's the common thread that causes the common event. Okay, so just like we did with arguments by analogy and inductive generalizations, why don't we practice with some causal arguments and we'll work on classifying them. So here's a short one. I had trouble playing that passage last night. It must have been Smith's funky piano. So we have to ask ourselves, is there a common event or an exclusive event? Is there something that happened over and over again or to everyone? Or was there something atypical or out of the blue? And I think you can identify that in this case. It was something atypical. And the effect was trouble playing, right? Trouble playing the piano. And so we have, we're on the lookout for the relevant difference, right? The cause of this. And of course, it's likely to be the funky piano of Smith. And this is relevant difference reasoning. Right, so again, in that example, there is a relevant difference that causes an exclusive event. The relevant difference is the funky piano, the exclusive event is trouble playing, and it's relevant difference reasoning. Here's another argument. I know it's crazy, but every time it's windy, the fish bite like crazy. So is there something out of the blue, or is there something that's kind of happening over and over again? Well, that every time is a clue, right? So it's the fish biting like crazy that is the common event. And the common thread here we think is the wind. So it's common thread reasoning. Okay, here's more kind of bad jokes, but so be it. I couldn't perform last night, honey. All I could think about was modus ponens and disjunctive syllogism. So this is hopefully something out of the blue, and so we're going to have an exclusive event, and that's not being able to perform, and the cause is going to be the relevant difference, and it was our mind being distracted by logical rules like modus ponens and disjunctive syllogism. So we have relevant difference reasoning. Here's something from the sports world. I can't change my socks, coach. We'll lose. Right? So sometimes you can interpret these in two different ways. So this one, there might be something that happens over and over again, and that might be the winning. Whenever you wear the lucky socks, then you win. So in that case, we would have a common thread causing a common event in common thread reasoning. The common thread would be the socks. The common event would be winning. Or you could think of this in terms of relevant difference, right? And that would be, so typically you win, but then when you took the socks off, you lost. So the exclusive event was losing, and the relevant difference was taking the socks off, and that was relevant difference reasoning. And that's okay, so there's no wrong answer in that case. But you can tell that some of these clearly fit into one of the two categories, and there are some, like this one, where you can frame it in terms of either, and that's fine. More bad. Sorry, I apologize for these. These are supposed to be sort of funny, but I think they work better in like a classroom setting. But oh well. So this is a joke from Austin Powers. Did you eat asparagus, Tim? The bathroom smells. So I guess urine can be smelly after eating asparagus. But I actually heard that some people have some people's systems are set up that they don't release whatever it is that causes this. So it's not everyone, actually. So you could be the lucky one and be immune to this effect. All right, so this one, it's that word again, right? It's like there's a pattern here. It's that the bathroom smells and we blame the asparagus. And so it sounds like a common event of smelly bathroom. And the common thread is the asparagus and common thread reasoning. You could frame this, I think, in terms of relevant difference, is that the bathroom usually smells fine, and all of a sudden out of the blue it smells bad. And so that smelling bad is an exclusive event. The cause was the asparagus, the relevant difference, and that would be relevant difference reasoning. So that's another one I think you could frame in multiple ways. But as long as you get one of them right, that's sort of what I'm looking for. All right, so we talked about classifying causal arguments. Let's talk about some mistakes that often are had when you reason like this. So before I go into the specific ones, just note that all of these philosophers say are examples of this fallacy related to causation that has this funky Latin-sounding name, the post hoc fallacy. And that's short for post hoc ergo propter hoc, which translates to after that, therefore because of that. In other words, because two things happen one after the other, we assume there's a causal relationship, but there might not be one. So that's the possible fallacy. That's the possible mistake. Other ways to frame this or think about it is because you think that X caused Y because X preceded Y. X came before Y. But just because things are paired with each other chronologically doesn't mean that there's a causal connection. And we'll talk about some examples. Or you could say X caused Y because Y came after X. You might have heard the adage, correlation does not necessitate or equal or entail causation, right? You learn that if you study subjects in the social sciences like psychology, right? Things could be correlated, and there might not be any causation. I mean, one example might be, maybe it's vitamin supplements that you get in pills. Maybe those don't really add to your health, right? I know that some physicians argue that a lot of times your body doesn't absorb the vitamins and you just kind of pass them through. And but if you looked at if you measured healthiness, right? So you could do a study or an experiment where you do an experiment where you get let's do a study. We'll talk about the difference between the two actually. So that's a good kind of mix-up that we almost had there. Let's say we do a study and we investigate the relationship between vitamins and a healthy lifestyle, and we notice a correlation between vitamins and a healthy lifestyle. So if we were reasoning in haste, we might assume that, vitamins must lead to a healthier lifestyle. There must be a causal relationship there, and you might think, that makes sense because your body needs vitamins, and especially in a lot of people's diets today, we don't get all the vitamins we need, and so that result makes sense. But as I mentioned, some physicians argue that most of the stuff in the supplements doesn't actually get absorbed, and so You might be ingesting 500 milligrams of vitamin C, but your body actually gets little or none of it. And you say, oh, if you eat it with food, then that helps, and that could be, but still there might be issues with absorption. And you might say, but Ryan, how could, look, we did a study and look at the correlation. There were people that took vitamins were healthier. But perhaps it's just coincidence. Maybe the correlation doesn't equal causation. Maybe there was a third factor. Maybe it's just that people that happen to take vitamins also just happen to have healthier lifestyles. They also had better diets and exercise more. And it was those things, it was the better diet and exercise that caused the on average healthierness, if you will, or I should say the better on average health. That makes more sense. And in the people that didn't take vitamins, it was their diet that wasn't as healthy and lack of exercise. So that's an example where correlation doesn't equal causation. So we have to be careful. These are really common mistakes. Okay, so let's look at specific ways that we can screw this sort of reasoning up. Sometimes you just miss the real cause because you're focusing on the wrong one. Like in the vitamin example, we're so focused on the vitamins because it seems like the obvious answer that we miss the real cause of the healthier diet and exercise and lifestyle. In our pizza party example, just kind of going with an outlandish possibility, we just assume that it was the pizza or the Mountain Dew or whatever, but maybe there's something strange going on that we couldn't anticipate. There was something, like in this extreme example, there's an evil demon that slipped something into our beverages, and we had a pizza party, everyone got sick, everyone's throwing up pizza, so we assume it was a pizza, but maybe it was something else. Another common mistake is when there's a third underlying cause that causes both the effect and the cause that is in question, right? So let's say that you assumed that that peppers made you sick, right? You ate some peppers, and then chronologically, right after, you got ill, right? And so you assume that it was the peppers. But maybe it wasn't the peppers at all. Maybe there was a third thing, right? So I say third because the peppers are a thing, you getting sick is a thing, and a third thing is something is in addition to those two. Now, I'm not saying that you're like, oh, I get it. It's that there's a third thing that caused you to eat the peppers that got you sick. No, I'm not saying that at all. I'm saying, because in that example, there's still a causal relationship between the peppers and getting sick. But what I mean to say is that the mistake here is there's no causal relationship between the peppers and you getting sick. Because, and in fact, there's a third thing that is causing both you to eat peppers and make you sick. Now think about that. What could make you sick and what could cause you to eat peppers? It's kind of tough. If you think about it, here is a good answer to that question. What if you are pregnant? Right? So we know, at least from the movies, assuming that that's somehow maps onto reality, that being pregnant can lead you to be sick, morning sickness or something like that, nausea. And also, maybe these are all stereotypes, but I'm assuming there's some truth to them, that being pregnant can cause the strange cravings that we've heard of. And maybe it can give you a craving for peppers. So the pregnancy caused both, and it wasn't the peppers at all. They did not make you sick. So if you could kind of get rid of the pregnancy and you just ate the peppers, you would be fine. Before we go on to this next example, I think the vitamin one also works in this, right? You thought that the vitamins caused you to be healthier, but in fact it was just your lifestyle that led you to make healthier choices, or what you thought were healthier choices, right? And that led you to being healthier, but it also led you to buy vitamins and take them because you, maybe you believe that they're good for you. And maybe it turns out that they didn't do anything, but your other choices, like better diet and exercise, they are the ones that caused it. So that would work too. Okay, let's go to this example. You thought that being smart made you need glasses. right? I mean, this is obviously an old stereotype that smart people wear glasses. Okay, so somehow being smart causes a need to wear glasses. But this is a common misconception. So what if somebody believed there was a causal relationship? We could say, no. There's a third underlying factor that's causing both. So what do you think could cause you to need glasses and also could cause you to be smart? What could cause you to be intelligent and also cause you to need glasses? I kind of like thinking about these because it's like a little puzzle. And if you think about it long enough, I think you can figure it out. What about your parents or your heredity or your genes, right? So the genetic factors that are part of your makeup could have a causal effect on your eyesight, right? Having poor eyesight might in part be genetic, and intelligence might also be due in part to genetics. So that could be a third thing that causes both, and that the intelligence had nothing to do with causing the need of the glasses. Now here's the third of four mistakes. Sometimes it's just coincidence, right? So there's so many examples of this that we fall victim to. Maybe you, here's one from my life that's just sort of a silly example. And, even after teaching this logic class and teaching critical thinking classes, I still fall victim to this stuff. So, how every once in a while you'll have, your ears will just kind of start ringing a little bit. Not from like being at a rock concert or something, but every once in a while you'll just get like a ringing in your ears for a few seconds. So when I was a kid, this really scared me, and so the way that I dealt with that is I would stick my finger in my ear and kind of wiggle it a little bit. And I noticed that every time I did that, it went away, right? And so I correlated sticking my finger in my ear and causing it to make the ringing go away. And it took me a long time to realize that, no, the sticking my finger in my ear did nothing to make the ringing go away. The ringing just went away on its own, like it naturally does, right? So your ears sort of reset, and whatever it is, some sort of self-correcting mechanism, and the finger was just sort of a distraction that kind of made me feel better. So it was just coincidence. It didn't actually cause anything. So that's a pretty good example of that mistake. And here's the fourth and final one. Sometimes the causation's actually in the other direction, right? So for example, which is the direction of causation in this case? Is it a backache that causes bad posture, or maybe your bad posture is causing you to have a backache, right? So on the one hand, maybe you slouch a lot because of laziness, and that leads to some pain because you're not standing up straight, and your vertebrae are getting kind of pushed together in a way that ends up being painful. Or it could be that maybe standing up hurts for whatever reason, right? Maybe you have some sort of defect in your vertebrae, and if you stand up straight, it hurts. And so the pain of it hurting leads you to slouch, which feels much better. So it might not be clear. I think another example is with drinking and feeling sad. So we know alcohol is a depressant, and it can lead to people feeling sad. And some of you have experienced people that drink a little too much, and they can get really emotional and crying and stuff like that. But we also know that being crying and being emotional and sober can lead people to drink. So it could go in either direction. Sometimes it's not clear what it is. And sometimes it's both, right? And to bring back Austin Powers, or maybe it's this Austin Powers 2 or 3, I forget which it is, but there's that character named Fat Bastard. And he says, I eat because I'm unhappy, and I'm unhappy because I eat. So in that case, the two things, eating and unhappiness, they feedback on each other, and they one causes the other and vice versa. And so this is sometimes described as a cycle, and more precisely as a vicious cycle. Or it's described as a positive feedback loop, because the cause in turn is also an effect, and it just keeps increasing and increasing. All right, what I want to talk about now is scientific reasoning. So this is something that we've been taught about. Luckily, it used to not, we didn't even know about it. It was invented or discovered. And now it's a part of classes in science that we expose children to. So a lot of this won't be new, but we still make so many mistakes because we ignore or we aren't aware of some parts of this. So it's good to kind of recap. So I'll try to do this quickly, as it will be a lot of review for a lot of you. All right, let's say that somebody claims a cure for baldness, right? And maybe they pay to have one of those late night infomercials to sell some miracle product to cure baldness. But maybe it turns out to be a household product. Maybe it's just red wine, right? So if you and it's not, I don't mean drinking red wine. I mean pouring red wine on like a bald guy's head will cause hair to regrow. So that's nuts, right? And let's say someone paid you to show that this causal relationship is not there. So you'd have to test this claim. This is a causal claim that red wine causes hair regrowth. Well, to do it, you should do an experiment, and we're going to you get two groups of people, and since the target population is bald men, there's millions of them, so we would want 1,500, right? That's the magic number, and we want them to be random. So we put 1,500 people into two groups, call one the experimental group and one the control group. And in the experimental group, we dump red wine on their heads. So we could load up some super soakers and just tell them to bend over, point their heads toward the experimenter, and just douse them with red wine. And then the control group, we would want to also be comprised of 1,500 men that are as similar as possible to the experimental group. And one way to get pretty close to this is just to do the random people. So if you get 3,000 random people and split them up, both groups should get to be pretty similar. And then the only difference is you don't expose them to the cause in question, which in this case is the red wine. And you might even use some sort of placebo, so you might fill the super soakers with water with red food coloring and maybe a little bit of vinegar to produce the odor of wine, right? And then after that, you would measure the difference between them. And if there was a difference, then you would conclude that it was likely due to the red wine. So I want to teach you just about the, let me go back to this. Sorry about that. I want to teach you about the term double blind. You probably have heard that before. Some of you might know what it means, but it's an important thing to know about if you're going to know about logic and inductive logic and scientific reasoning. So when somebody says an experiment is double blind, what that means is that the participants of the subject, they don't know what the hypothesis is. And actually the people that are implementing the experiment, they also don't know what the hypothesis is. And the reason why this is good is because when participants know what's being tested, they have expectations. And expectations are powerful, and they can affect our psychology dramatically, and they can skew the results. So it's better if in the red wine bald case, you might just say, oh, we're going to test, you make something up, like, oh, we're going to test memory, right? We'll give you some pairs to remember, like train grass, a wood, metal, pencil, calculator, and we want you to remember the pairs, and then we're going to just shoot you with a super soaker with red wine and see if that helps memory. So we don't tell them that's actually about the baldness. Now, expectations in this case probably won't affect hair growth because that's something that is tough. But if it was a study and we asked people just to report their own, does your hair feel thicker? Then expectations could totally come in. So if you give someone a pill, this is also known as the placebo effect. You give someone a pill that, and you say, this is going to make your hair grow, and then a month later you give them a survey and you ask them, does your hair feel thicker? They might report yes, even though it's all sort of in their head. And it's also good for the experimenters or the researchers not to know the hypothesis. Because when they're tabulating the data, they might have some wishful thinking. They might hope that the results come out, especially if it's a product they're testing that they eventually want to sell. They might kind of skew the results. And a lot of this is unintentional. People want to be objective, and they just kind of naturally can't do it as well when they know what the hypothesis is. So that's what a double-blind experiment is. So both of those, the observer effect and the placebo effect. The observer effect is when my behavior changes when I'm being observed. All right. There's also observer effect in quantum mechanics, but that's neither here nor there. But I just wanted to say that. Okay, then I said we measure the amount in both groups and compare, and if there's a big difference, if there's more hair growth in the experimental group, then we could say, oh, and it sounds like this. It doesn't prove, but it confirms that red wine might have an effect on hair regrowth. Now, sometimes we can't do an experiment, right? It's impractical, or it's unethical, or it's too costly, and so we do a study. Let's say we were trying to figure out if a lifetime of a fatty diet causes colon cancer. Think about what we would have to do if we were going to do an experiment to show this, right? We'd have to put people in a lab for their whole lives and subject them to a fatty diet, and so that's impractical. It's all these things. It's impractical, it's unethical, it's too costly. So instead of doing an experiment in this case, we could do a study. Studies often are just handing random people a questionnaire or a survey. And so in this questionnaire, we'd ask these questions. 1, have you lived a lifetime of a fatty diet? So we'd have to define what that means. We could say, it's over 65 grams of fat per day, and then kind of people don't know what that means. So you might say, and a hamburger typically has 25 or 30 grams of fat. Or I'm making up numbers, whatever it is, to give people a sense. And then they would say, and you could measure it on a scale of 1 to 9 or something. And the second question, could be, do you or have you ever suffered from colon cancer, right? And then you look for the correlation between them. Again, we could still have the two groups, the experimental group and the control group. And in the experimental group, it would be people that have answered affirmatively to question 1. And in the control group, you want people as similar as possible to those people. So we call it experiment. I know the name is misleading, but we'll just use the same terms for consistency. Even though it's a study, there's no there's no experiment done. But so let's call it the experimental group. And the control group, you want to be people as similar as possible to the people in the experimental group, but they just haven't been exposed to the cause in question, in this case, the lifetime of a fatty diet. And same thing, you measure and compare the difference. Now you might see that it's much harder to establish causation with studies. You get some information, but the best way to offer evidence for causation is is a double-blind experiment done properly. So here's some differences. Experiments are done in controlled environments like a lab. In an experiment, the researchers expose the subjects to the cause in question. So in the red wine example, it was actually the researchers that are shooting the red wine with the super soaker to the bald man's head. But in the study, the cause in question is just naturally part of the participants' lives. Okay, and because of these two things, there's a less chance of extraneous variables or they're called confounds, in experiments. In a study, there's a greater chance of these extraneous variables, and thus the results of experiments are inherently stronger. They're more accurate, reliable in studies, and better predictors of causation than studies are. Okay, so that was a lot of review, but it was still important, and so even if it was just a refresher, it's something that is good to be reminded about. All right, let's talk about dubious hypotheses. So what that word dubious means is doubtful. And this is a term that the authors use in our textbook. And the reason why they don't put false hypotheses is because, it could be that these hypotheses turn out to be true. It's just we should we should raise an eyebrow. We should be careful before accepting them. We should be a little skeptical. And you'll see what I mean as we go through these. So the first kind is called a circular hypothesis. That's where the effect is really just a restatement of the cause. So let me give you an example of that. Say you went to the doctor and you say, doctor, I just can't sleep. I haven't slept the last 3 days. I don't know what's going on. Can you figure out what's going on here? Is there, take up some blood, run some tests. Is there anything like physiologically going on that's causing my sleeplessness? And the doctor, examines you, runs a bunch of tests, and then a week later he says, "Aha! I've discovered the cause of your sleeplessness. You have insomnia." It's like, well, that's what insomnia is, it's sleeplessness. So that's not really a cause. That's just restating the effect with different words, right? So that's not very helpful. Let's say, I can't write. What's going on? Oh, you have writer's block. Oh, okay. But that's not going to help you. I mean, think about in trying to cure these things. It's like, oh, how do I fix my sleeplessness? Oh, well, just don't be an insomniac. Oh, how do I write again? Oh, well, just don't have writer's block. That's not very helpful. But if sleeplessness was caused by some maybe taking you take too many naps during the day. Now that's a cause, and that's something you could change. So that's why when you put it that way, you can actually do something about it, but not in these circular hypotheses. So again, it's not that they're false. Actually, all of these turn out to be true, but they're just kind of meaningless and trivially true. They're not very informative or interesting. So that's the first one. It's a circular hypotheses. Second one, or if you have an hypothesis, by the way, the hypotheses is not a typo. That's the plural of hypothesis. Same thing with if you have one thesis, but if you have multiple, then you have theses. So that's just you've probably heard that before. If you can't test a hypothesis, then it's not that it's false. It's just doubtful. If there's no empirical way to verify it, then you just got to be so careful. You should just kind of be agnostic to it. For example, people, very hateful people have had signs that with big bold letters say that AIDS is God's wrath. And is that true? I mean, a lot of us don't believe that it's true, but there's no way to figure that out, right? I mean, unless you could kind of talk to God, and maybe some people claim they can, but barring that, how do you figure this out? There's no way to test that. Here's an example I give to all my classes that I really like that's less controversial than this AIDS God's wrath one is, let's say it said that when no one's looking, and let's say that there are no recording devices of any kind, that all the trees in the world, they uproot themselves and do backflips. And then the second you turn your head to look at a tree, it puts itself back into the ground without even an iota of evidence, right? There's no, that sounds silly, but it could be true, and there's no way. How would you prove that that's false? How would you just confirm that? There's no way to do it, because the only way we would have to do that is by, watching trees, sitting in a tree and watching and see if it ever does it. And that's exactly when they don't jump. And you say, well, I'll set up a camera. Well, they know about the cameras. Their trees are smarter than that. And then you could say, well, we look for evidence that they did it when no one was looking. Well, the trees are smart. They don't leave any trace behind. So that could be true. There's just no way to test it. So this is related to a kind of reasoning called self-sealing. Self-sealing, a hypothesis that is guilty of self-sealing reasoning is when it will virtually sound any sort of counter-evidence. Let's say that, suppose we have a class on natural disasters, and we talk about Hurricane Katrina, or we talk about the earthquake in Haiti, and somebody asks, what is the point of this? What's the meaning of all that suffering? So many people suffered, so many people died. What's going on? If there's a point to life, it just seems, it doesn't make any sense. That when there's suffering on that level, it just doesn't seem to make any sense with a lot of our beliefs. So what if someone said, this is a common answer, that there exists a God, and God has a plan, and we're just too finite and too dumb, to be blunt, to understand God's plan. God's a being, at least according to definitions from many Western religions. God's a being with infinite wisdom and infinite intelligence. He or she's it's omniscient, and this is all part of a mysterious, beautiful plan. And God would tell us, but it would be pointless because we wouldn't be able to understand it. It's very the saying, God works in mysterious ways, kind of captures that. So that could be someone's answer. Why did all these people die in Haiti? Well, God works in mysterious ways. So we can't really know the answer, but rest assured, have faith that it's part of God's plan, and don't let it keep you up at night. Now, is this true? Is this false? I don't know, but it could be true. I think as a logical thinker, you have to be open-minded. But there's no way to test that. And one thing that would make it more difficult to hold on to such a hypothesis is if the natural disasters started to increase. What if they started increasing exponentially? They just started increasing in frequency, and all of a sudden we're having earthquakes every day, and people are dying left and right, and the human population is dwindling and dwindling and dwindling, and then let's say eventually we go extinct like the dinosaurs, then if things got worse and worse and worse to as bad as you can imagine, notice that you could still use this answer. You could still say after every natural disaster, after all the death, after every single one, you could say God works in mysterious ways. God works in mysterious ways. And so there's no sort of scenario where that wouldn't work. And if a hypothesis is sort of immune to any sort of opposition, then that's questionable, and that's why it's kind of sealed itself away from any sort of attack. That's why it's called self-sealing reasoning. Okay, and so that's essentially what I said. And the last note there is, there's a famous philosopher of science who was named Karl Popper, and he argued that if it's going to be a scientific hypothesis, then it has to be falsifiable. And what that means is that it at least needs to be, in theory, there needs to be a way in theory to disprove it, right? So, even a law is false. It sounds like falsifiable, sounds like false. But even take, like a law of, F equals ma, force equals, or no, do not get that complicated. Take the law of gravity. The gravitational, gravity, bodies accelerate toward the center of the Earth at a rate of, 9.8 meters per second squared. And so that's a scientific law, right? The law of gravity. And but in theory, there's a way to disprove that, and it would be simple, right? You just measure a bunch of things falling, and if they started to fall at different rates, if they started to fall faster, if they were bigger, or if on Tuesdays they fell faster, then we would have to then the theory would be false, and we would have to adjust it. So there's ways to disprove it, but with the God works in mysterious ways, there's not even a way in theory to disprove that, right? Okay, we got a few more here. Here's the third dubious hypothesis: if it conflicts with established theory. So what does that mean? Well, take this example with height. So we have an established theory that how tall you are is going to be, at least in part, determined by your parents, right? By your genes, right? We know that height is closely related to genetics. Maybe not totally, your environment, so you could, a simple example would be you're 6 feet tall, and then your legs get severed off, and now you're not 6 feet tall anymore. So that's how environment might come into play, but there are less crude examples of that. But we know that for the most part, your parents and your genes and hereditary are very important for height, contributing factors. So that's the established theory. So here is a theory that conflicts with that. Now, again, I use kind of an extreme example just to make the point. Maybe there's reincarnation, and in your past lives, if you did good things, then you're taller in this life, and if you did bad things, then you're shorter, or vice versa, right? Not to say that, maybe if you did good things, then you were short. I'm not to place any value on height. So that's an extreme example, but just to make the point that when a theory conflicts with something that's very well established, it's not necessarily false, it's questionable. That's another synonym for dubious. Because remember, sometimes a theory that runs against the grain of the established theory can end up being correct, and it can end up replacing old theories. Take Newton's laws. For hundreds of years, Sir Isaac Newton's laws of motion were thought to be perfect and that they would never be refuted. And then lo and behold, Albert Einstein came around with his theory of relativity and showed that Newton was false. His laws were false, at least in some respects. And so Einstein's theories are now the standard and replace Newton's. But at a point, Einstein's theories conflicted with the established theory. And again, it turned out to be true. So we just have to be careful, and good scientists were careful. Einstein knew this, and you have to repeat the experiment. Repeatability is a tenet of science. Do it over and over again, confirmed by different scientists all over the other worlds with different goals and objectives. That helps too. Galileo's heliocentric theory of planets orbiting the sun conflicted with the geocentric theory that the sun and planets orbit the Earth. So, as lots of you know, thousands of years ago, people believed, or even hundreds of years ago, people believed that the Earth was the center of the universe. So geocentric, geo meaning Earth. But that, and then when Galileo came around and offered evidence that this is the case, that it was actually the Earth that is orbiting around the sun, which is the heliocentric model. Helio is for sun, so there's helium and sun, it's related. There was a conflict there, and it turned out to be true. So again, just because it's dubious doesn't mean it's false. It's just questionable, and we should be careful. Okay, so I want to talk to you about Occam's razor, which is also you don't want to conflate these, but they're closely related. The principle of parsimony. Parsimony is when things are kind of neat and simple, and they're not overly unnecessarily complicated. So William of Ockham was this middle-aged philosopher medieval philosopher who argued that good hypotheses should be simple and they shouldn't be unnecessarily complex. So it's also spelled Ockham with 2 C's. The way he phrased it was it was in Latin, so this is the translation of the Latin from him originally. Entities must not be multiplied beyond necessity. But the way that it's often kind of phrased today is like this, which is sometimes called the principle of parsimony. Given 2 hypotheses that are in all other respects equal, the simpler one, the one with the fewer assumptions and posits fewer entities, is most likely the correct one. Right? So in short, the simplest explanation is often the right one. You probably have heard that before. So that's an echo of Occam's razor, or the principle of parsimony. So let's use Occam's razor with these 2 hypotheses. So we talked about height being related to your genes. We also know eye color is very much genetic. So here is a theory that completely just throws Occam's razor out the window. It's completely complicated. It just seems unnecessary. What if I said that, no, eye color isn't your genes. It's determined by the eye color fairy. And this is how it works. There's this fairy, and then there's this eye color wheel. The fairy spins the eye color wheel. But every once in a while, the fairy's decision on your eye color could be vetoed by the eye color dragon, right? So it's a complicated theory. Think about, our whole worldview would have to be expanded. We have our physical realm, but then we have to posit a mystical realm where there's eye color fairies and dragons, and there's magic, and this whole process of selection and veto system, etc. And it's just much simpler just to go with what's established. So a lot of time, that's why I included this after conflicts with established theory, because if you do that, then you're immediately not being mindful of Occam's razor. Okay, that is the end of the final lecture. I hope that things went well, and just kind of a short recap on what we did. We talked a lot about arguments, right, and what goes into a good and bad argument. A lot of the class was the mistakes of arguments. That was all the fallacies, and we talked about what goes into good arguments. Arguments are deductive or inductive. And so now we know what goes into a good deductive argument. It's got to have all true premises and be valid. So we spent a whole section of the class learning a formal way to show if an argument's valid. If it's an inductive argument, then we need to look at sample size, and we need to look at how similar the sample and target are. We need to look at representation. And we need to be careful to be mindful of all the things we just learned about causal arguments, like common mistakes and the doubtful hypothesis and the scientific method. And then we also talked about the kind of logic path, the logos-pathos distinction. So the logos non-logos, which is good inductive deductive logos versus non-logos, which is fallacy, and then logos pathos distinction. How much rhetoric and colorful language can affect our psychology and how powerful that can be. And so all those rhetorical devices and rhetorical fallacies. In addition to that, we just learned to be looked at the logical nature of our relationship with ambiguity and vagueness, and being precise with definitions. Okay, hope you had a good class, and I will see you around.